My name is Kikuchi from Keysight Technology. Thank you very much for giving me an opportunity to speak to you. And now I would like to give you the presentation titling the Publishing the Envelope in Quantum through TE Innovations. And I would like to discuss about the products that they have released last month, and which is quantum bit control solutions. And first, I would like to talk about the history of our companies. And in 1939, Hewlett and Dave Packard, and as a Hewlett Packard companies that we have built, and since after that, for the 80 years of the history that we have, and in 1999, there was a separation of the company, became the Agilent Technologies. In 2014, the measurement divisions has become the Keysight Technology. And then this is the QCS, the world's first fully digitalized quantum control systems and hardware, PXI form factor, as you see here, and digitizer, the converter, and those kind of modules, including the waveform generators, and that has been established with the PXI modules. And in terms of the software, the Python API is equipped with, and it will be easy to use this. And in this presentations, what is the advantage of the current other type of the solutions? And I would like to discuss about what is a merit for the research and development of the quantum computers, which I would like to describe. In a QCS, and there's three characteristics, and one is the high performance, and the second is the future-proof scalability, and the third is the ease of use. And I would like to go one by one. And the first point, and I would like to discuss about high performance, and QCS from the Keysight, and that has been fully digitalized. And our digital innovation, QCS is not the first ones. And due to the customer's requirement, starting from the 2005, we have started the development of the DC converters, or MMICs, and then we have developed the ASICs, and the first time in the world, outputting the microwave directly with the digital. In 2009, UX Agile, the signal generator, that has been released. And for this one, the frequency and the power can be switched in a shorter time with the direct microwave output. And QCX, and with that, this the technology was used, and furthermore, the advanced technology was used. And for the quantum bit, the microwave paths is used, and that can be directly outputted in a digital manner. And now, with this slide, I'd like to discuss about what is the advantage of outputting with the digital. And in a quantum digit control, several gigahertz control, the microwave is used. But usually the digital and analog combination is used, and with the digital baseband path is outputted with the IQ mixer, which is analog, and there is up conversion with the frequency of the hertz. And there's two issues. And the first one, and there is going to be distortion, and therefore the left-hand side you see the spectrum, and this is the multi-tone, and with the distortion and the leakage, the dynamic range, which does not have the impact of the spurious, is going to be reduced drastically. It needs to be suppressed with the calibration. And the second is the impact from the drift, and therefore this distortion and the leakage is going to be deteriorated after some time, and therefore the periodic calibration needs to be required. On the other hand, in case of the fully digitalized way, the IQ mixer equivalent part is going to be done. Digital the calculation or computations, and that output through the DA converter, that is going to be outputted. And without the IQ mixer, and therefore, in terms of the distortion and the leakage will not happen, and nor the drift impact. And the right at the bottom, there's a spectrum, and compared to the analog, the digital one is less impact of the stream as, so that you can get that the large volume, the dynamic range, without the impact. And the A converters, and the left-hand side, and this is a custom DA converter ASIC has been developed. And based on this technologies, and you see the right-hand side, and for the first time, and this M300A was developed, and with the 2 gigahertz, the signals, and through the from the DC, the 16 to the wide range of the frequency that we can cover in the output, and the height is 13 centimeter and 4.4 centimeter width, and 21 depth. The compact form factor, and with the 4-channel microwave can be outputted. And I would like to show you with the example. And now there's a 4 the waves, and the blue is a digital, and the green is analog. And right at the top, digital IQ, and left-hand side, 3 gigahertz digitally outputted wave, and with IQ, and then also 3 gigahertz a wave, and moderated, and you can see the middle the waves. And with the QCS, it can be done digitally, and then after that, the A converter and low pass filter will be used. And a Gaussian the type of the microwave health is going to be outputted. And conventionally, with the IQ mixer area, there was a distortion and leakage, and needs the calibrations. However, in case of the QCS, and there is no need for the calibration. And digitally, it is connected directly in the 4. In case of the equal bit, we can actually reduce that the phase the noise. And in case of the analog system and PLL, and in case of the digital method DDS, there's a differences of those two. In case of the PLL, and there's accumulation of the noise, and the 4 it will be deteriorated. And in case of DDS, it's going to be act as a divider, and the noise will be reduced. Accordingly, the phase the noise will be improved. And from here, I'd like to talk about the second uniqueness of the QCS for the future the extensions. And in the quantum computers, the qubit numbers needs to be increased, and therefore we need to consider about the extensions. With the QCS, in order to support the extensibility, and there are 3 technologies that we've been used. First one is the Keysight unique frequency is the standard, and among the researchers, our PSG, and this has the high phase the noise performance is used as a standard, and this standard is equivalent to the PSG signal generator, and the PXI search we can incorporate it into it, and that is very compact. And the second point is that from this from here we get the standard the clock, and it can be distributed within the system overall at the low phase noise, and the system and overall it can be used. And the third is that digitizer modules or the waveform generated, the hardware sequencer is separately implemented, and we can synchronize with that. And with those 3, and from pulse among the pulse, and there's coherence, phase coherence, and then also the multiple modulars. This kind of phase coherence can be maintained. And time-based real-time run is possible and can be synchronized with the multiple channels. And at maximum 80 of the PX chassis, it can be supported with those technology. And this shows using the QCS from 500 to the 2000, the qubit bit is controlled in the system. And from 500 to 2000, the qubit number covers large numbers. because the lead out, depending on the multiplication of the frequency divisions, that's all depending on that. And therefore, as you see here, and the multiple chassis is used, and it's not supported yet. However, we will develop the softwares so that we can support this using QCS. The multiple quantum bit is used, and if we are thinking about this way, in that case, please let us know. And with the QCS, there's the third ones, and easy to use. And from the hardware point of view, with the not the IQ mixer, and digitally, the signal is modified. So IQ mixer calibration is not necessary. And then also, because no calibration with the IQ mixer, and therefore, there's no periodic downtime. As you see here, among the multiple module it is used, and it needs to be synced. And for each module, there's a hardware sequencers dispersed. And there's the triggers signals inside, and therefore, it can be automatically done. And here, there's a two fixed chassis extensions. And in this case, even though it is easy to do it, and the cables and the numbers of the cables and numbers of the signals, you may think that it's a lot. However, the two, there's only three that you needed, and one is from the host PC control cable, and the second is the blue, and this is for that's in this chassis, and this is a reference clock division cable, and the third is a flat cable, as you see here, and this is for the synchronize. The trigger single is going to be divided into the three. So even though with the more chassis, it's still easy to sync. Now, QC is easy to use, not just for the hardware, as well as the softwares. That's how we have it designed. In case of the Python API, from the starting point of the development of QCS, the quantum application was focused. And for the researchers, it will be easy to use. And also, with the FPGA, it can be speed up. And second is that hardware and also the connection among the qubits, that you don't really change it. And then also, in the other area, you can actually split easily, such as like pulse sequences. And the fourth, the maintenance is easy. And the rows has been drastically reduced. And the third is the database support. And the first application outcome is the stored in the database, and you can actually use it for the testing. And this is the QCS, the Python code overview. Left is the static, the system configuration, and this is the path configures definitions, and then after the calibrations, and this is going to be the values, and the right-hand side part sequence definition example. And this is the main part, and per sequence output is like this, and this part, the is 0.5, and then after that the 300 onsec weight, and the phase, the 90-degree slip, and at the end the pulse is outputted and the measure. And this is the example of the sequence. So intuitively, and you can describe the per sequence. One of the software perspectives, using the FPGA, it is easy to handle. When you say FPGA designs, for the many of the developers, it's pretty hard to use it. However, FPGA block that can be quite often used, and that is in the libraries, and therefore you can use this library. And even though you don't really know about this, you're not familiar, but still, with the shorter the latency processing and those kind of things that you will be able to get it. And this is using the Ramsey per sequence example and tape recorder method. And among the pulse to pulse, and there is a delay, and gradually you may have to increase. And in that case, one by one, you have to create the different waves with the little increment, and you have to load it. And therefore, the numbers of the delay, if there's a more, and in that case, 2. So with the loading time, and that required the lot. And that was one of the issues. In case of QCS, you don't need to do it. And then, because only the pulse primitive can be loaded. And then, in terms of the delays, at the hardware sequencer, they triggers, and then you can adjust. And therefore, the pulse numbers or the wave numbers, and then also the time can be reduced drastically. And this is at the digital side, and this is a signal block, and that also prepared like this. And reading qubit and provide the filters and can be converted into the IQ signals, and from there to decode to the qubit. And that is kind of filter, and therefore you can customize this filter at the customer side. And that decoded outcome, and it can be read in the PC, and at the same time combining with the pulse primitive, depending on the decoded qubit status, you can switch this pulse for the next outcome in a dynamic manner. And before I summarize, let me give you the overview of the main module of the QCS. And the first one, the M5300A, RF8WG, and in the red box, and the 2-slot PXI modules, and the 14-bit. Excuse me, from the DC 16 gigahertz, and also the bandwidth, the 2 gigahertz. And the Vortex Ultra Scale and FPGA, partially you can customize it. And this is a down converter and digitizer pairs, and the 4 channels, both of them. Down converters and 2 gigahertz to the 16 gigahertz signal can be entered for both of them, and the 2 gigahertz for the down converter as well as the digitizer. Digitizer as well, same as the AWG, Vortex Ultra Scale FPGA is on, and therefore the customer can customize a part of that. At the end, I would like to summarize the reason why you need to select the QCS in shown in here, collaborations and software and support from that perspectives. And we are focusing on the quantum area very much, and therefore we will continue to develop the solution in this area. And from the software, the programming, the language, is a Python that's generally used for the control. And multiple chassis, multiple modules, because the qubit number is going to be large volume, and a phase and that can be synthesized, including amplified, hardware digitally modified, and with the DX. And at a real-time basis, you can update the frequency as well as phase and skew, as you see here, and then also the stabilization of the amplifier output. And that's also all stabilized for a longer the experiment. It will be stabilized. And with this, I would like to conclude my talk. Thank you very much.